This video is going to be about Pythagorean tuning. We're going to look at how is it constructed, why is the piano keyboard laid out like it is, which note is the best one to tune from, what is the allowed range of values for tuning that note, what is the recommended value for tuning that note, and why is Pythagorean tuning significant? Number one, how is it constructed? The circle of fifths. This is my favorite book on the subject, A Beginner's Guide to Constructing the Universe by Michael S. Schneider. Everything you're about to see is taken from Chapter 7, Enchanting Version, the section entitled The Geometry of Music. So to start off with, we're going to start with a circle of diameter 1. We're going to create a dyad out of that circle, and then we're going to circumscribe a new circle around that dyad. If we measure that diameter of the new circle, we see it is 1.5, or 3/2, which is the perfect fifth. So anytime we create a dyad, the diameter increase from the circle it's being originated from will always be in the scale of a perfect fifth. So we can do this a second time. We can create a new dyad out of that new circle and circumscribe a third circle around that and take its diameter. So now what we've done is we've taken a perfect fifth of a perfect fifth. And we can do this again. And we can do it a fourth time, a fifth time, a sixth time, a seventh time, an eighth time, a ninth, 10th, 11th. At this point, we now have 12 different diameter lengths. I'll refer to them as string lengths from now on since we're talking about music. On an interesting note, if we were to take away all of those original circles and just leave ourselves with the dyad construction circles, they make an interesting pattern that almost looks like a kind of a sonic sound wave. And if you actually put a line tangential to all of those circles, it turns out to become a perfect equilateral triangle. All right, the name of this channel is Quadrivium432. We always like to try to look at how the quadrivium can be applied to real-life experiences through number, geometry, music, and cosmology. And in this case, we're going to be looking at cosmology. We just created 12 lengths of string through number, geometry, and these are, because they're string, it's applying to musical scale. Now we're going to look at cosmology. What we can see here is something called an orbital resonance of Mercury. It has a 3-2 orbital resonance where for every 3 Mercury years, 2 Mercury days will pass. We also see the perfect fifth in orbital resonances around different star systems. This one here is HD 110067. The first 3 planets are all in orbital resonance of 3/2, and then followed by a few orbital resonances of 4/3, which we will see later on as the balanced twin of the perfect fifth. Is called the perfect fourth. In the TRAPPIST-1 star system, we also see some planets that have orbital resonances that are perfect fifths. We also see some other fractions, such as 5/3 and 8/5. We'll talk about those fractions in a future video. All right, so why is the piano keyboard laid out like it is? So we just measured out 12 string lengths using the circle of fifths. We're going to play a game now. And in step 1 of the game, we're going to pick any string and make an octave from it. I'm going to go ahead and pick the first string for now because going from 1 to 2 is about as simple of an octave one can do. So it should be the most illustrative, but we're going to do them all here before long. So step 2, we're going to halve or double as needed any string that falls outside of the established octave until it falls within that interval. So we can see the first string, 1.5, it doesn't need to be halved or doubled at all. And that's going to be true for all perfect fifths. Then from down there, we will need to eventually halve everything until it falls within that interval. Step 3, arrange all of the newly created values in ascending order. So we start with 1 at the top, and then we go ascending until we get to 2 at the bottom. And we have everything in order. That's that right-hand column. Step 4, find all of the multipliers between each of the values by dividing any value listed with the value above it. So if we do that, we get some recursive multipliers there next to that column there on the left or on the right. And we see there are only 2 recursive values that ever come up, and they come up in a very distinct pattern. And the pattern of the 2 possible multipliers between each of the values mimics the keys on the piano keyboard, which is based on the Pythagorean scale circle of fifths. The first value generates the B scale. Okay, so that first string, when we look at the pattern it creates there, we can line it up with a keyboard, and it goes from B to B. I've also added some extra information now to this. We have a median line drawn. We're going to look for some significance around that. We also have a boundary line drawn, which lets us know how many times we had to have or double something before we were able to get it to fit within our interval. And if you notice here, I flagged 2 particular intervals. The perfect fifth always comes below the octave, and it never needs to be halved or doubled. The perfect fourth, however, in this particular arrangement is not perfect. It is an expanded fourth, and as you can see, it requires the most halving in order to achieve, and it's as far away from the octave on here as one can possibly get. They are literally on polar opposite sides. So let's see what happens when we do the next string. When we do the next string, we see its pattern corresponds to the octave of E. Now we're talking string lengths here. So this would be the equivalent of what the string lengths on the piano would be, not the frequency. We also see something else peculiar, and that is now we see a perfect fourth. A perfect fourth will always be directly above the octave on this line here, and it only ever will need to be doubled once. That will be true for perfect fourths from now on. So the perfect fifth never needs doubling. Perfect fourth only needs to be doubled once, and they always fall on either side of the octave. So when we do the next string, we find out it corresponds to A. The next string corresponds to D. The next string, G. And now here we are at the median, and this string length corresponds with C. And this is kind of interesting because our median line has 6 above it and 6 below it. 6 terms. So the first 6 terms containing all of the whole notes ends with the C scale. This puts the C scale in the median of all possible constructions of the circle of fifths. So it's middle C. And what we notice about middle C there is its perfect fifth goes over the median line into sort of the next area there. So it's like a bridge in a way to the other half of the musical strings that are being created here. Another thing interesting about this particular string here of C is it requires the least amount of halving or doubling of all of the string lengths. You can see here we're only going to double something 3 times, or we're only going to halve something 3 times. And this is the only string length where you have that phenomenon happening. Everything else is going to have 4 or more of either side. So when we look at the next string, it corresponds with F. Now, B through F are all the white keys on the keyboard. We call those whole notes. But F falls on the side where all the sharps and flats, the black keys, fall, as we're going to find out here. So if we keep going down, now we have A sharp, D sharp, G, C sharp, and finally F sharp. Now this one's got some color going on. In the video on Equal Temperament 12, we determined that the F sharp octave was the one that closest corresponds to an octave of light. So here I tried to approximate the color of what that would be in the light spectrum using Excel's color palette. And just like we saw with the string of B, the very first one we did, where its expanded fourth was on the exact opposite end and required the most amount of halving, here at F sharp, since the perfect fifth always falls below the octave, well, the octave here is on the bottom line. There is nothing below it. So what happens is its perfect fifth kind of folds over to the other end in form of the contracted fifth, which is called the wolf comma. And it corresponds to the line there on B. Being furthest away from the octave, it also requires the most amount of doubling. So true Pythagorean tuning has no Pythagorean comma. What happens if a 13th term is added from the circle of fifths? There is a belief that the circle of fifths must be continually repeated up the keyboard, which, if done, will result in a gradual octave misalignment. This is due to the Pythagorean comma, which is the difference between a true octave and the value derived from the 13th term of the circle of fifths, which is very close to 2, but slightly larger. If one tunes this way, the recursive pattern will no longer coincide with the keyboard pattern. Remember the rules of the game? Any number must be halved or doubled until it fits into the true octave interval. Therefore, 2.02728663 hasn't been fully halved, and would obviously not qualify if it was halved, as 1.01136438285 makes no sense as an interval in this tuning system. The proper way to construct Pythagorean tuning is to build a recursive list from the first 12 terms of the circle of fifths, and then repeat that pattern up and down the keyboard. If the Pythagorean comma occurs, then the tuning is wrong. This is why understanding recursive patterns in music is so significant. Using Pythagorean tuning, the keyboard was clearly constructed to conform to this pattern and not the other way around. It settles the age-old riddle of which came first, the chicken or the egg. The answer is the egg, or in this case, the Pythagorean tuning recursive pattern. Which note is the best one to tune from? All right, in my video on equal temperament, we showed how if you tune any particular tone on the octave of F sharp 4 to a whole number, you will eventually get very, very close to a convergence point between hertz and nanometers. We showed a conversion in that video. So I'm going to do this real quick. I'm just going to go down the line here. We'll look at what the maximum value is for each of these tones, and we'll figure out through the error list on the 2 columns on the right which one would intuitively be the best. All right, here we go. Boom, boom. Here we go. Yay, boom, boom. More numbers, and stop. Okay, this is what we come up with. C5 is the winner. Now, if you look, most of them tied at 0.68% error. That's average error. And I could have expanded the decimal out until they eventually separated out, but the reason why I'm keeping track of 2 different kinds of errors here, the first one is the average of the absolute value of the error. The second one is the sum of whether the values are positive or negative to see how close it gets to 0. And you can see if we look at both of those, C is the clear winner. C may have tied with all the rest in the absolute value, but when it comes to the non-absolute value summation of the error, it gets the closest to 0. So C is going to be the value we tune off of. And if you look here, we have a box around B4 just below C there, and that's going to play a part here in determining our next thing. What is the allowed range of values for tuning C? Well, we know what the maximum is now. It's 538. And if we look at that B4 value of 511, well, we can't tune C to 511 because all we've done at that point is just shift the scale up the keyboard by, 1 semitone. and then we're just right back where we started. Just everything's shifted. And we can prove that here. If I tune C to 512, you can see there are no values when C is 512 that are equal to or less than what those values would be when C is tuned to 538 if we look at the values that are shifted down by one semitone. Whereas if I tune C to 511, now you can see we have notes that match. So we've essentially just kind of shifted the scale, and we're kind of back to where we started. So 512 is the minimum. Also, we talked about mapping light and sound in the first video, and here it is. If you're curious about RGB values for Pythagorean tuning, you would tune it to 522, which gets you an A value as close to 440 as one can get in Pythagorean tuning if we're tuning off of C. What is the recommended value for tuning C5 within the interval of 512 to 538? So we're going to tune C5 for each value in the interval 512 to 538 inclusive and count all whole numbers generated for each tuning. The value that yields the most whole numbers will be the recommended tuning. So you can see here, we're not counting the seed value that we're tuning, which is 512 in this case, but we're going to count all the whole numbers it generates to the first octave. So you can see here, I highlighted them in green, and there are 6 whole numbers that are generated when C is 512. And if we do that for all those values, here's what we come out with, a chart. 512 is the winner. You get 6 whole values when you tune C to 512. So if we look here at everything, there's something that's just kind of noteworthy. I put the digital roots at the top of each of the columns just for curiosity's sake. Digital root, of course, means you add up each of the digits of a number, and then whatever the first single digit number they add up to is, that's the digital root of that number. So 512 is 5 plus 1 is 6 plus 2 is 8. So that gives a digital root of 8. And 538's our other maximum value. And then if we look at the median value, it's 525 there. 525 doesn't really, it's not very significant in this system. Now, if we look 3 units below 525, we get that RGB value there, 522. And what's interesting is if we look 3 digits above 525, we get a solfeggio number of 528. And that corresponds with the first runner-up of who gets the most whole numbers. It gets 5 whole numbers. So it's kind of interesting that the solfeggio number comes in second place. All right, so now that we have our keyboard laid out, we have all of our recursive patterns entered, we know which note we're tuning off of, and we know we're going to tune it to 512. We put it in, it generates all of our numbers. And what we notice here is all the white keys, which we call whole notes, those all generate whole numbers. Isn't that a coincidence? Now the exception here is F. F never generates a whole number. And neither do any of the black keys, any of the sharps or flats. They always generate non-whole numbers. So in this case, F behaves like a black key, even though it falls on a white key. Now, quick primer on intervals. An interval is defined as you start with any kind of a baseline tone on the keyboard. It can be anything. You refer to that as the unison, and then you play a second key, and you count how many semitones away it is from that unison, and that tells you what your interval is. And we talked about that in the equal temperament video. So what we're going to do here is we're going to examine what all of the different absolute intervals are in every octave on the keyboard here. And what I've done is I have on that top keyboard laid out where all of those intervals are, starting with the unison, going all the way to the octave. And there are particular colors that I've done here. Those blue ones, the unison, the octave, and then we have the major second and minor seventh, and the perfect fourth and perfect fifth. Those are all blue because those are all key intervals, and I want to kind of look for any significance that might occur with those intervals in particular as we go up the scale. So if we look here, the F4 octave where we're starting is one of 2 octaves where every interval uses the dominant multiplier. The only distinguishing factor is that it uses the tritone multiplier that is generated by sharps. It is also the only whole note that does not generate whole number values. Okay, so that's everything significant about F. And if we look here, okay, we can see that there are some black key values that generate white tones and white key values that generate black tones, and some of those intervals fall on black keys and some of them fall on white keys. So, okay, nothing really significant going on. Then we go to F sharp. The F sharp 4 octave is the octave that best contains an octave of light, or the full color spectrum visible to the human eye. And what we notice here is it has a lot of expanded and contracted fractions. All those red fractions, those huge fractions, those are all offset fractions. They're not the default or the dominant intervals. All right, then we go to G. Then we go to G sharp 4. It's the only octave where all 5 key intervals fall on black keys, and they're generated by the recursive multiplier that falls on a white key. So that's kind of interesting. There's a interesting pattern there. And then conversely, the A4 octave is the only octave where all 5 of the key intervals fall on white keys and are all generated from the multiplier on a black key. The A scale is the second most significant scale in Pythagorean tuning, called the minor scale. All right, so here's minor scale. It actually has something significant about it, which is this pattern here. All right, and then we keep moving on, and we keep going. All right, now we get to C. The C5 octave is one of 2 octaves where every interval uses the dominant multiplier. The only distinguishing factor is that it uses the tritone multiplier that is only generated by whole notes. The C scale is the most significant scale in Pythagorean tuning, called the major scale. All right, and we keep going up the keyboard, keep going up, looking for patterns, taking notes, making tables, and we're done. This is an addendum that I made after finishing the initial video. We're going to ask ourselves, are the black keys sharps or flats? Okay, so here we are. We have A and B with their respective sharp or flat between them. Is that A sharp or B flat? And if we look here at the patterns, we can see that there is a mirror, reverse, inverse relationship between every whole note and its flat twin. There are no relationships with any whole note and its sharp twin. So let's look at what's going on in this particular slide. At the top, what I have is each counting of a black key group that I see. So A has 1 black key and then 2 black keys and then 2 black keys in that octave of A. Then we look at the octave of B flat and we see those numbers at the top, and then we see the octave of B and we see the black keys it contains within that octave. And then down below I have the mode of the octave here and its name. W stands for whole, H stands for half. It's the pattern of whole steps and half steps you take throughout the octave from start to finish. We're going to look and see if there's any significance we can look for in either of these sets of numbers. But if we now look at the pattern of those 5 key intervals that we just talked about in the prior section, we can see here B flat has a stronger correlation with the pattern in B than it does with A for sure. You can say that A, it's all blue, the blue multipliers, and with B flat, it's all pink ones. So a case could be made for that, but you'll see later on that A has a better flat. But in this particular instance, what we see here is we see 3 long pinks that turn into 3 short blues on B, and then 3 of these kind of lower down pinks that turn into higher up pinks in B. So there is a certain kind of a transformation, but it follows a uniform pattern in both instances. Okay, so is the black key D sharp or E flat? And when we look at the pattern, we see that this one is much more obvious. We see those 4 long pink lines in E flat turn into short blues in E, and then we see kind of that lower pink turn into a longer pink in E. So definitely a strong correlation and pattern there. All right, is this black key G sharp or A flat? And this one in particular is very interesting. So what we see here is, I pointed this out in the prior section. This is what was the spark of inspiration for me to go ahead and take this extra step of analysis. But the A flat pattern is obviously all these long pinks where every one of those key intervals falls on a black key. It's generated by a multiplier on a white key, and they follow the keyboard pattern perfectly. In fact, we have 3 groups of 2 black keys there. And then what we see in A is we see the exact same thing, but mirror opposite. All of the key intervals occur on white keys, and they're generated from the multipliers on the black keys. And we can see this is definitely about as mirror image as it gets, or inverse or reverse or whatever you want to refer to it as. And it should also be noted that A flat there is kind of a convergence point of mirror symmetry. If we look at the black keys at the top, we see a pattern that clearly is mirror inverse of each other. We see 2-2-1 with G, and then 1-2-2 with A, and then A flat has all 2s. So that mirror symmetry is really right there at that center 2. And we also look at the 2 different modes, Mixolydian and Aeolian, and we see a mirror symmetry in the whole steps and half step pattern that occurs there. This seems to be, in all the flats and whole notes, a particular point in the piano that is a significant point of convergence. So I made a note of that. All right, and is this C sharp or D flat? And we see once again very clear correlation and pattern there. And then we have, is this F sharp or G flat? And once again, very clear pattern correlation. All right, so finally we're left with F and C. And we have F and C are not preceded by black keys. So we have to ask ourselves, do F and C have a sharp or a flat? And I postulate that F and C have, since they have no black keys, they are actually linked to each other. They each have identical structures, if you look, except for that perfect fifth there in the center, which are opposites of each other. And then if we look at the black key pattern at the top, they also show a mirror symmetry here of 3-2 and 2-3. Their modes, however, are not mirror symmetry. However, it is very interesting to note how F and C are almost identical to each other, and therefore I consider them to be bridges. They bridge, in my opinion. And we're going to explore that a little bit later on. But for now, just kind of keep it in the back of your head. Okay, so this image here, we're going to look at this in more detail later on in the video. But for now, what we want to notice is, of the 2 columns, the white keys on the left and the black keys on the right, if those black keys were to be considered sharps, then in order for us to link each whole note to its sharp, we would get a pattern like this. And we would get something where B would link up to C as its sharp, and F would link up to F sharp there at the end. So essentially they're referencing a note within their own group, which I would say is a violation, similar to the vertical line violation in algebra for determining whether something is a function or not. I'm going to postulate something similar here, where the vertical line test means it doesn't pass muster. However, if we consider the black keys to be flats, then we do not get any violations. We get a clear correspondence between each of those white notes on the left with each of those black notes on the right, F being the exception, but we also noted that F is like a bridge. C and F, they bridge. And we also see that A and A flat correspond with the same location on each column as well. So once again, we noted that that was a particular point of significance on the keyboard, and that is reflected here. So to me, this image here completely sums up Pythagorean tuning. We'll look at it a bit later on in more detail. Okay, but for now, what I'm going to assert is that the black keys clearly show a reverse relationship as a whole note's flat, not sharp. They also make more sense as flats in the symmetry of Pythagorean tuning structure that we just saw. As such, black keys will be referred to as flats from now on in all slides and in all of my videos. So as this addendum section comes to an end, I want to state that I feel that I have adequately proven that the circle of fifths generates the recursive fractions that the modern keyboard pattern is built around. There is no Pythagorean comma, and by extension, no expanded or contracted octaves. The expanded fourth and contracted fifth are separate intervals from the tritone. All tritones are either expanded or contracted relative to both equal temperament 12's value and each other. And all black keys are flats, and neither C nor F have flats. I'm sure all of these things are going to be very controversial to a lot of people out there, but I think the math demonstrates this is all valid. All right, so we're looking, here's a quick refresher on geometric means. Geometric means are whenever you multiply any number of factors together, then you take the nth root of those factors, depending on how many of those factors you multiplied. In this case, we're only ever going to be multiplying two factors together, so we're always talking about a square root, and we said that those two factors have to multiply together to equal 2. And we can see from our first video on equal temperament that the geometric means on either side of the tritone mirror each other, and they conform to that rule. So here what I've done is I've created tables of all of those absolute intervals that we generated from that prior exercise. So we're looking here at the minor second and the major seventh. So those are in geometric mean balance with each other. If you multiply any fraction from one side with a corresponding row on the other side, they will equal 2. And we can see here which ones are expanded and which ones are contracted, and we can also look at a little bit more as to why. For the minor second, at the top I have the mathematical purity value listed, which is 2 to the power of 1 over 12, and it rounds to 1.06. I'm rounding everything to the nearest hundredth. We can look at all the values for the minor second generated by Pythagorean tuning, and what we get is we get a small fraction, relatively small, 256 over 243, and it occurs 7 times. So the smaller fraction occurs the most number of times. I refer to that as the dominant fraction, or the default fraction, either way, or the primary fraction. And then you have some kind of an expanded or contracted version in that same interval. In this case, the minor second, it's expanded, and it's a larger fraction that occurs less frequently. And compared to the dominant fraction, it is greater than 1.07 rounds. It rounds to 1.07. It is a larger number than 1.05. So we call that expanded. And everything you're going to see in the one is going to be mirrored opposite on the other. So for every expanded in the minor second, you'll see a contracted in the major seventh. Now at the bottom, I have standard deviation numbers listed. This tells you as a whole for all the minor seconds that can be generated in Pythagorean tuning, if we compare that to equal temperament, what is the error? And we can see that it's 0.71%. standard deviation for minor seconds, and 1.26% standard deviation for major sevenths. All right, so just keep that in mind as we look at all of these. I won't spend as much time on the rest of them, just wanted to let you know how to interpret what you're seeing. All right, so here we have the first set of significant intervals. We have the major second and minor seventh. And as you can see, these are extremely dominant, and the fractions on them are also extremely small. Conversely, their expanded and contracted versions are very, very large. So even though they are few and far between, when they do occur, they are very large. And we see lower standard deviations here than we did with the prior interval pair. So now we have the numbers for the minor third and the major sixth. We have the major third and minor sixth. And then here we have the perfect fourth and the perfect fifth. And now you can see why these are called perfect. Basically, every single interval of perfect fourth and perfect fifth is dominant, with one and only one exception, and that is the F sharp octave. When we go from F sharp to B, that is a expanded fourth, and then when we go from B up again to F sharp to complete the octave, that is a contracted fifth. And in fact, that contracted fifth has a special name. We call it the wolf comma. The wolf comma is not a flaw. It is a necessary correction that the entire system relies on in order to maintain symmetry and balance. Similar to how we have a leap year, where we add an extra day to the calendar. It helps to keep the calendar in phase with the slight error that starts to occur over time. The wolf comma does this. It is a correction that helps the system to basically stay in balance. And as you can see here, it is the largest fraction generated in the Pythagorean tuning system, and it happens to fall in the interval section of the smallest fraction possible, 3/2, the perfect fifth. Now we have the tritone. The tritone is interesting because the tritone has no other twin interval. It is the boundary, and it is its own self-contained geometric mean opposite. As you can see here, we have 6 versions of 1024 over 729, and they correspond with 6 versions of its geometric mean pair, 729 over 512. And this is almost reminiscent of when we talked about the tritone in the equal temperament video, how it's based on root 2. And the root 2 rectangle is the only rectangle that, when split in half at the midpoint of the longer side, creates 2 smaller rectangles with the same root 2 tangent as the parent rectangle. So there's a self-replicating fractal holographic nature to root 2. And we see a semblance of that here in the tritone, where we have a microcosm of the whole music system contained within just this interval here. And you can see all the pairs that I've colored out there. So there is no dominant fraction in the tritones. However, I think you can still say that there is a default tritone of the 2 pairs. And if we look here, there are 2 octaves, and only 2 octaves, where every interval they have is a dominant fraction, F and C. And what I've listed here is you can see what all the dominant fraction values are, and there is a pattern where if you look at the numerators, they slowly increase in size until you get to what would be the logical tritone of 729. And it follows a pattern of, when you look at the denominators, there's a denominator that's a power of 2, followed by a power of 3. 2 and 3 all the way down, and the 729 over 512 tritone conforms to that pattern. And likewise, the offset fractions always start with the largest numerator, and they descend until you get to the logical conclusion of the 1024 over 729. Because the C octave has the geometric mean inverse tritone, it breaks that pattern. So I'm going to posit that the tritone for the F octave is the quote-unquote default tritone. And it happens to be the tritone that not only F, but all of the black keys are based off of. So the proper default tritone is what all the black keys are based off of, and the non-default tritone of C is what all of the white keys are based off of. So it's kind of interesting that the one could see as the flawed tritone generates all of the tones that generate whole numbers, and the good tritone, so to speak, generates all of the octaves that generate non-whole numbers. Sort of a yin-yang thing going on. All right, another quadrivium alert here. The tritone reminds me a bit of the crossover cable in computing. A crossover cable, when you want to network two pure nodes without using a router between them, you have to rewire your cable in crossover fashion so that the two nodes can communicate with each other. And at one point I was thinking about this, and this came to my mind, how a chromosome is shaped reminds me of this structure. So chromosome has a centromere in the middle, and it has a longer arm and a shorter arm, and it's also bisymmetrical. And when we look here, if we were to put the C octave and the F octave next to each other, we have all of the default dominant fractions listed on both sides, but where C and F differ is they have swapped tritones. And it sort of reminds me of where the centromere in a chromosome would be. Also, if you have a musical scale on the left there, we have a guitar bridge showing where all the different intervals would fall on a geometric scale. And we see it almost lines up with exactly where we would expect a centromere to be in a chromosome. So I think there is something not too far off about that correlation. So, summary of the Pythagorean music construction. In the video on equal temperament, we talked about the mystery of squaring the circle. We talked about how the circle is the mathematical ideal, where the square is the best rational approximation we can make of that mathematical ideal in our real world. Equal temperament 12, being an irrational music system, cannot be created accurately in our world. It can only be approximated through rational means. And the Pythagorean tuning system is our first attempt at doing that. So it's our first attempt at squaring the circle, so to speak. And if we put a line graph of the two on top of each other, we can see how well Pythagorean tuning is able to approximate equal temperament 12's pure mathematical curve. And you can see it wobbles around a bit. We have a total standard deviation of 0.60% error. All right, so here we go. Here's our comparison chart. We're comparing equal temperament 12 to Pythagorean tuning. Is it rational? Yes, it is. In fact, it is the most primal rational music system one can develop. For recursive multipliers, it has two recursive multipliers that follow the piano pattern. Its geometric mean default octave. This is how many octaves does it use, have perfect geometric mean relationship, which means it uses all the default fractions, no expanded or no contracted intervals. And that occurs in two octaves, F and C. The only way they differ is they have opposite tritones. Does it use small default fractions? No, it does not. Only the major second and minor seventh and perfect fourth and perfect fifth have small, what I would call a small default fraction. All those other default fractions we saw, they go all the way up to 256 over 243. That's kind of a big fraction. Not impossible, but certainly unwieldy. What is the best tuning for whole numbers? We determined that C5 is the best note to tune from. We determined that 512 Hertz was the best value to tune it from. That is a binary number. It gives you 6 whole numbers. And as far as standard deviation goes, we determined that its standard deviation is 0.6, which is fair. It's not the worst we're going to see. And when it comes to mapping Pythagorean tuning with light, we determined the best value for C was 538. And if we have 538 for the maximum value, that makes 512 the minimum value. Okay, so why is Pythagorean tuning significant? At this point, the math is done. We're going to talk more about philosophy, and I'm just going to interject my own sort of observations about the patterns that my brain is able to detect when I'm examining this musical tuning system. In Chapter 4, Mother Substance, the section called The Birth of Depth, Michael Schneider writes, "The tetrahedron is the only three-dimensional shape whose corners are the same distance from each other. Buckminster Fuller considered the tetrahedron to be the basic unit of space. While the sphere encloses the most volume in the least surface area, the tetrahedron encloses the least volume with the greatest relative surface area. Being the minimal solid, it is the strongest and most stable. The birth of the tetrahedron, the first volume, brings the triad's principle of triangularity, stability, to 3 dimensions using the fewest materials." So here's some information about the tetrahedron if you're interested. So Pythagorean tuning, which I submit should be rebranded as tetrahedronal tuning, it is the most primal tuning system possible, in that it is maximally stable using minimal materials. It is the only musical tuning system to be entirely binary in nature, including actual binary values for C. It uses 2 smallest prime numbers based in all fractions, powers of 2 and powers of 3. It uses 2 fractions for recursive multipliers, 256 over 243 and 2187 over 2048. It has 2 possible fractions for all intervals. The fraction with the highest frequency is the default dominant value and has a smaller numerator denominator. The other fraction is the expanded or contracted relative to the default value. It has 1 pair of possible geometric mean inverse fractions for the tritone. When matching recursives to the keyboard, 2 octaves, C and F, show perfect default fraction geometric mean inverse relationships within all intervals. The F octave, however, uses the 729-512 tritone, while the C octave uses the 1024-729 tritone. C5 equaling 512 generates the most whole numbers octave-wide. Every whole number corresponds to a whole note. Each whole number, except C, is a factor of a power of 2 and a power of 3. The C note's binary value can be halved all the way back to 1, or unity. This octave and its specific interval sequence is referred to as major key. When matching recursives to the keyboard, the A octave is the only octave where the 2187 over 2048 recursive fractions line up with the key intervals of the major second, perfect fourth, perfect fifth, minor seventh, and octave, which are all on white keys. This octave is referred to as minor key. So we have 2 main keys in this as well, major key and minor key. And the circle of fifths generates the modern keyboard layout. Okay, power of 2 and power of 3 significance. Every aspect of the Pythagorean tuning system relies exclusively on generating all numbers using a power of 2 and or a power of 3. This is a table of all whole number Hertz values generated for all the whole notes, excluding F, because F never generates whole numbers. The interval 1 through 24 occurs only in theory as it extends beyond the left side of the keyboard. It is derived by halving all the allowed whole notes until they arrive at their root power of 3, assuming they have one. So we can see there at the top table, we have powers of 2 going along the column headers, powers of 3 along the row headers. all of the numbers they generate. Gray numbers occur in theory. All the other numbers are actual numbers that occur on the piano keyboard. And then I also listed them in the bottom according to ascending order. It is also significant that the entire range of the 88-key standard keyboard starts with not just any power of 3, but 3 cubed, or a measure of volume in 3D space, immediately followed by a binary. Only 2 notes, C and G, do not generate a digital root of 9. All polygons, and by extension all 3D platonic solids, have angles that add up to numbers that have a digital root of 9, also known as the horizon number. The 88-key standard keyboard ends with a binary for a boundary, specifically 2 to the power of 12. Another name for 12 is the convergence number. Binary digital root sequence significance. All right, so if we look at the digital roots of the binary numbers at the top, we can see they all add up to 6 numbers, 1, 2, 4, 8, 7, 5, and then it repeats after that. When arranged as 3-digit numbers, they generate all those different 3-digit numbers there, with the final one being 512. A fractal holographic type of self-reference occurs at 512. It just happens to be the tuning for C5. And it also happens to be 2 to the 9th. 9, of course, we just already talked about, is the horizon number, occurring just before a break, gap, barrier, or boundary in a process. The word horizon is derived using the name of the Egyptian god Horus. We'll talk about Horus in a bit. The first instance of a pure power of 2 on the 88-key standard keyboard occurs at 2 to the power of 5. The last allowable power of 3 on the keyboard is 3 to the power of 5. There are boxes around the octave associated with light. The gray box next to it is where the first instance of a theoretical 3 to the power of 6 would be. Interesting that the octave for light occurs just before that break, gap, barrier, boundary in the pattern. Musical interval significant numbers. If looked as musical intervals, all the Hertz values in the gray area make perfect fifth, perfect fourth, and starting with D, major second intervals. The octave, perfect fifth, perfect fourth, and major second are all generated by adding 1 to a prior number, always a pure power of 2 turning into a pure power of 3 or vice versa. So 1 plus itself is the octave. The octave plus unison is a perfect fifth. The perfect fifth plus unison is a perfect fourth. And if we go up to 8 and add 1 to that, to get to 9, we get a major second. And those are the only times where a binary and trinary value occur next to each other and are separated by 1 unit. Fibonacci significant numbers. All intersecting Fibonacci numbers except 144 occur in the region of theoretical numbers before the actual keyboard starts. The numbers 12 and 24 are linked to the digital roots of the numbers in the Fibonacci sequence. The unit circle is also split up into 24 theoretical sectors. 12, 24, and 144. Both 12 and 24 have a connection to the Fibonacci sequence. 144 is 12 squared and is a Fibonacci number that occurs at the 12th Fibonacci term. 36, 72, and 108 are all degrees associated with the golden triangle and golden gnomon. 54 is the degree used in the trigonometric equation for calculating phi. And then, of course, we have 432. In sacred geometry, all of the shapes associated with structure, function, order are present. The triangle, square, hexagon, and dodecagon. These are all shapes that are easy to create with a compass and straight edge. In Chapter 4, Mother Substance, in the section entitled Back to Square One, Michael Schneider writes, the ancient Greeks noticed that 4 is the first number formed by the addition and multiplication of equals. 4 is equal to 2 plus 2, which is equal to 2 times 2. And so was considered the first even number and the first female number. Chapter 6, Structure, Function, Order. in the section Construct the Dodecagon. 12 is divided by 3, 4, and 6, the only three numbers whose shapes, triangle, square, hexagon, tessellate, covering a flat surface without leaving gaps. This is why 12 is sometimes referred to as a convergence number. All right, and up in the right-hand corner, we see the magic square. The magic square is a 4x4 square. It's the only square whose perimeter equals its area, which are both 16. If a circle is inscribed within a magic square, that circle will also have a circumference that is equal to its area, which is 4 pi. If lines are drawn from the center out to each point where the circle intersects the square grid, it marks the corners of a dodecagon. Adding lines from the center to each of the diagonals creates a perfect unit circle. All right, so here we have tessellating equilateral triangles, which you can also see. You can see there are hexagons in there as well. And then we have tessellating squares. Okay, so here we have the two tessellating shapes of hexagon and square, and when laid over top of each other, we get the unit circle, or if we carry it out to its logical conclusion, the compass rose. And here is the unit circle. And we're going to look at the unit circle in more depth in a future video. But for now, you can see that there are some fractions here that we have already seen. We have 3/2. Pi there is one of the values, 4/3 pi, and we also have lots of instances of 3/2, 1/2, or 2/2 in all of the coordinate systems. So, kind of interesting. All right, so we're going to look now more at the structure underlying Pythagorean tuning. Here what I've done is I've put all of the intervals, spread them all out into one cohesive shape, and I have put solid squares over any of the expanded or contracted values, what I call an offset fraction, and we're going to examine this. So in the center, we have the tritone. It has the most number of offset fractions at 6. And what we notice is that the tritone, being the most dissonant, it's flanked on either side by the two most stable intervals of the perfect fourth and the perfect fifth. And then what we see is the second most dissonant values are right there on each of the edges. And they're kind of walled out by the second two most perfect intervals, the major second and minor seventh. And what that does is it almost kind of keeps those dissonant values sort of separated out so that you create this Goldilocks zone in the middle of the minor third and its pair, the major third and its pair on the other side, and then the perfect fourth and its pair on the other side. Those are the ideal consonant areas. And I don't know, this kind of reminds me of like fusion containment and maybe people wanting to make fusion containment a reality might want to integrate vibration of some kind using intervals based on this in order to better contain the fusion reaction in the center. Maybe electromagnetic containment and sound containment in tandem would help the process. All right, here we have the actual structure of Pythagorean tuning as I have laid it out. And what we see here is we see two columns that I've circled in green. The column on the left is all of the white tones that generate whole numbers and share the offset tritone. The column on the right contains all of the black keys, as well as all of the keys that generate non-whole number hertz and share the default tritone. Then what we see at the top is we see a row that is circled in red, which contains both C and F, they are the two that share all primary interval fractions, right? They have all of the default dominant primary intervals in them. They only differ in the tritone, which that's kind of the crossover between the two, the bridge, so to speak. And then what we also see at the bottom is we looked earlier how that first dyad construction of B had the expanded fourth associated with it, and B, as far as string length is concerned, generates all of the binary string lengths. And then F sharp, it has the contracted fifth, and it has a string length. Its contracted fifth falls on a binary string, which is B. And if we look here, the F sharp octave from F sharp to F best encompasses an octave of light. And to tune this octave of light, we tune off of C, and we tune C to a binary number. So lots of interesting binary interactions happening in Pythagorean tuning. And when I look at this structure of how this musical system is generated, things start coming to my mind. In a documentary series called Magical Egypt, they talk about the churning of the Milky Ocean. And it is a story where you have a mountain called Mount Meru, and on one side are the gods, the Devas, and the other side are the demons, the Asuras. And they both are playing tug-of-war with a snake, going back and forth, spinning this mountain in a milky ocean. And by cooperating in this manner, they are able to generate treasures from the ocean to the benefit of all. And we almost see that being mirrored here in this musical tuning system of a tug-of-war between light and dark that ultimately generates in treasures. We see in Freemasonry the two pillars, Yahim and Boaz, the pillar of light and the pillar of dark, which frame a gateway. It was originally the gateway to the Temple of Solomon. And here we see in Egypt the gateway of Thebes, which you can see actually has 5 levels of the gate until you get to the top level, the 6th one, which bridges the top of the gateway, where the winged disc resides over. Kind of an interesting correlation. And here we see the tree of life from the Kabbalah, Jewish mysticism, which Freemasonry is inspired from. And you have, once again, the pillar of light and the pillar of dark in the Kabbalistic tree of life. And the tree of life, as you know, it also has a central pillar that the light and the dark revolve around. And that's very similar to the statue of Ramses, where Ramses himself is the central person with both the god of light, Horus, the god, he's associated with the sun, and the god of darkness there, Set, on his left side. But yet he exists as a perfect balance between those two. And here we see another version of this in what's called the Semitawi, which is the unification symbol of Horus and Set around a central pillar or object. And that's very similar to the Semitawi that happens in our own brains. Our right lobe is responsible for everything that happens on the left side of our body, and our left brain lobe happens to be responsible for everything that occurs on the right side of our body. And those two lobes are bridged by something called the corpus callosum, which is very similar to how the tritone seems to bridge the two lobes of this system. And we talked a lot about the yin-yang earlier, and it just goes without saying that the yin-yang can also be a microcosm of the human body, where you have The brain lobes being the dots, and the swirls of the yin-yang being similar to the body, where the one lobe controls the other body and other side of the body and vice versa. And we see how in this system the tritone definitely acts as the dots of the yin-yang. And I'm sure anybody studying the system might be able to find all other myriad of associations with it, but those are some of the main ones I came up with when I have meditated on this musical structure. And the final significant thing that I will posit is this keyboard. The keyboard pattern modeled after the Pythagorean tuning recursive multiplier pattern is the de facto keyboard for all 12-tone music tuning systems from here on out. It is generated by powers of 2 and powers of 3. It also has a link to the Fibonacci sequence. It is the necessary geometric scaffolding for approximating the mathematical purity of equal temperament 12. And here you can see in Chapter 5, Regeneration, the section called The Rabbit Riddle. Michael Schneider writes, "The piano keyboard is a metaphor of accumulating vibration and so is structured by terms of the Fibonacci sequence. The 13-note chromatic musical octave consists of 8 white keys, whole tones, and 5 black keys, sharps and flats, arranged in groups of 3s and 2s, making one full octave." In the end, what is significant about Pythagorean tuning? Everything. What I learned by studying Pythagorean tuning. Symmetry is built into the universe. The universe has no flaws, only corrections which are necessary for the whole system to function. The universe is designed so that creating light cannot occur without also creating dark. When light and dark interact and cooperate, they create beautiful music. The universe is simultaneously balanced while also ensuring that light always has a larger presence than dark. And here's mother and father. They never seem to be able to get along. If there was only some way to get them to reconcile. Oh wait, there is. Find out in future videos. Thank you for watching.